All right, everyone, and welcome back to HDL for Digital System Design. So today, really quick, this video, digital logic refresher, much shorter than the last one. So let's dive right in the sense that why does this matter? You've probably seen gates or at least high-level logic in other classes. This is just calibration. Make sure we're on the same page with names, truth tables, symbols that we'll see throughout the rest of the course. Just want to make sure that we are on the same page. So big things that are different. We are looking at gates through the lens of what does Verilog build? The ampersand, the AND operator, is an AND gate. The question mark colon, the ternary operator, it's a mux. Every single construct in this course maps back to primitives in this video, um, so it's important. So what you should know, and if any of this is completely brand new to you, or you just don't remember, please do take time to go into a deeper dive refresher here. So basic logic gates that we have: and, or, not, NAND, NOR, XOR, and XNOR. So also Boolean algebra. Be comfortable with De Morgan's distribution, complements. You want to be able to know how these work. Uh, might not have come up or might not always remember combinational versus sequential circuits. Combinational is essentially if everything can be determined by the current state of inputs, that's combinational. If history or the current state matters, right? So if it's inputs and the current stored state, then it's sequential logic. It means that you must have some amount of memory, some ability to store information. So combinational or purely combinational circuits are just a function of their inputs. Sequential logic is a combination of inputs and stored state for what is the next state. Truth tables, essentially bidirectionally equivalent to Boolean expressions, right? So can you go from a truth table to Boolean expression or a Boolean expression to a truth table? Being able to do that is important. All right, understanding what a D flip-flop is, essentially it captures the value of D, the input, on a clock edge. So what gates are you going to see the most? These four. So what we'll see is the symbol, the word on top as well. You'll see what happens for low voltage 0 and high voltage 1. And then remember that these gates are just physics-based devices, right? They are not some metaphor to anything else. They are physics. So, AND gate, two inputs for the basic one, A, B, output Y. Symbol that gets used in Verilog is the ampersand. So A and B, both of them have to be true or high voltage for the output to be high. The OR gate, essentially either of them, right? So A or B, which means A can be on, B can be on, both can be on for the output to be driven high. The NOT gate is just flip the result, right? So if A is 0, the output is 1. If the input's 1, the output's 0. XOR, the exclusive or essentially the caret, right, is essentially different. Are the inputs different, right? So if it's if they're both 0, then the output 0. If they're both 1, the output 0. If they differ, so A is 0 and B is 1, or A is 1 and B is 0, then the output is 1. Making sure that we've got all these covered. The NOT was the tilde, and the OR is essentially the bar, right? Vertical bar. Okay, NAND, NOR, XNOR are just these same logic gates, right? And, OR, and XOR with a NOT bubble. So the output is knotted, right? So they're the same gates, just with the complementary outputs. So you can imagine knotting, right, on the AND here to get an output of 1, 1, 1, and 0 to do a NAND. For NOR, the output would be 1, 0, 0, 0. For an XNOR, it would be 1001, right? So it's just the nod of the output for the NAND, for the negated versions of these. So fundamental to what we're doing here, our gates can be composed. So you can imagine that we have desire to add two 1-bit numbers, 1 plus 1. So 1 and 1 in binary ends up making 1, 0. And so we would want maybe a sum bit and a carry bit, right? The sum of the two plus the overflow carry. So you can imagine writing a truth table, right? I've got A and B, right? So we've got A0011, B0101. The sum for these, right? When both are 0, we expect the sum to be 0, carry to be 0. When either one of them is 0 and the other one is 1, the sum should be 1 with no carry. When both of them are 1, well, the sum of both is 0 and the carry is 1. So we can describe that, right, as two separate, basically logic gates, right? So the sum ends up being an XOR, right? You can see that right there. And the carry ends up being the AND of those. So you can see the sum and the carry ends up forming this circuit that we see at the top here. That's it. That's the whole circuit. So we created a 1-bit adder using two basic fundamental logic gates. You can imagine that if I wanted to do this with a larger number, let's say a 32-bit number, I would just chain these together. So that is all we do in this course. We compose primitives, name them, and reuse them. So that is what we will do. So we will take this, we'll wrap it, and we'll name it as a module and reuse it. So we will wrap this up and reuse it to create a full adder. So talk about the translation from gates to Verilog. Well, wire, digital logic, is essentially assigning an AND gate is that ampersand symbol. An OR is the vertical bar. The inverter NOT is the tilde. XOR gate is the caret. And a 2-to-1 multiplexer. So I've got two signals and I want to choose between them, right? The equivalent of maybe a if then else or on a Boolean split. That is essentially right here, your select question mark true or false branch, right? So select is how you choose your branch, and then you're going to go either A or B is how that works. D flip-flop, the general way that that's going to work is we're always going to look for when a clock signal hits, take the D value that we have and store it into Q, right? Latch it into Q is the official term there. We can make expressions that combine and compound. So we could do a sum of products expression here of y equals AB plus CD, right? So here we go. We've got y equals A and B in parentheses, or C and D. Definitely possible. Also important to recognize that I can write things different ways and have the same logic defined. So if I were to create y1 is equal to not and then A and B, right? That is equivalent to me writing not A or not B, and it will create the same underlying hardware whether I do the top or the bottom. So under the hood, the reason why they're going to be the same thing under the hood is the synthesizer is going to optimize what you write. Its job is to take what you've written and to map that in the most efficient way possible to the hardware it has available to it. So goal here is generally write for readability and try to have your tool that you have, right? And this is why there's commercial tools, create minimal hardware. So your goal is to write so that you understand what's happening. Right, we've already seen these gates in Verilog, but let's take a quick peek one more time at what this could look like. So took example 3 from the lab here, and it basically asks to implement combinational logic between buttons and LEDs. And so just for fun here, LED 1 on when both switch and switch 2 are pressed. So you can do an assignment of switch 1 and switch 2. You can also do other statements like OR statements, right? Or you could do the XOR between two. You can also invert them. So ran this through, all right, and I went quickly because it's part of your lab, but so those were just different operations. I did a simulated version here. And now let's also take a look at the fact that it used 4 LUTs to do this. Well, I had 4 logical expressions, right? And ended up using 4 different LUTs to fit all these in. Um, all right. Ultimately, no errors, and we passed our test case that was defined in our test bench. And so what we can do is we can do make program here. And let's see if when I press 1 and 2, I believe I should get one LED to show up. And I do. And if I remove my finger from one of them, it goes off. And I put it again, and it goes on. I remove my finger, and that first LED goes off. Now, you've got to ask yourself, why are the other LEDs doing what they're doing? Well, that depends on how I've programmed everything and the logic that we've set up. So one of these is controlling this fourth LED and is always the inverse of whatever the button is on. So let's see. Let's see if pressing button 4 does anything. Doesn't change the last LED. Button 3 doesn't change the LED. Button 2 doesn't change that fourth LED. So button 1, I assume, is tied to the inverse. We'll double check that in the code here. When I press button 1, it turns off. Now the question is, why does LED 3 turn on when I press button 1? Well, perhaps there's some logic that's set so that when button 1 and something else are on, LED 3 will go on. So again, the point here is that if I press all 4 of these, all the logic is active in terms of I can do any combination of the buttons. There's 16 different combinations of how I can press these buttons, leading to 16 results, which are pretty unique across all of them. And so you can actually see that in our waveform as well. But it is all driven ultimately by how everything is defined in these 4 assigned statements. Okay, so going back real quick. We'll build up on this again over the course of the semester. Reminder that combinational logic, no clock, no memory. It's what we're going to focus on from the beginning. Sequential logic, clock driven, has a memory. We'll see it roughly later this week, just so you can get a hang of it and can see it. But again, that's the major difference. All right, so in theory, you should already know the hardware. Right? At some level, gates, Boolean algebra, truth tables, flip-flops, whether you're electrical engineering, computer engineering, or computer science, you'll at least have a firm grasp on hopefully at least 3 of those, hopefully all 4. We're going to talk in this class about the language used to describe that hardware. So you could ask your favorite AI agent, given a 3-input multiplexer truth table, write the minimum Verilog using a sign and the conditional operator, then tell me how many LUTs it will take on an ICE 40, ICE 40. Mux design, you basically could give it exactly what I just said. You could try to predict, right? 3-input mux has 3 data plus 2 select equals 5 inputs, doesn't fit on a LUT, so 2 or more LUTs is what it claims. You could verify how many. And I will tell you that AI can write correct Verilog, but it can't always predict how many LUTs. So the tool is ultimately going to win. So just know that. Okay, so before we meet for class in person, or if you're doing this on your own and want to spot check yourself, try to answer these questions. So pause the video after each one of these, see if you can answer it. What are 3 fundamental differences between writing software and writing Verilog? Go ahead and pause. All right, so 3 big ones. Execution model, sequential versus concurrent execution. Two, resources. The more code you have in the Verilog space, it's going to yield more hardware versus in software, it yields more time. Um, in hardware in Verilog, there's no dynamic allocation. Once you have hardware, it's fixed at synthesis time, and that's all you can do. All right, questions 2 and 3. And again, take a pause here after I've said them so that you can try to figure them out yourself. What happens to pound 10 during synthesis? What about during simulation? All right, can you write a complete Verilog module that connects switch 1 to LED 1? All right, pause the video, see if you can do these both. All right, so the answer, simulation, is going to wait 10 units of time. In synthesis, that statement gets completely ignored. That's why you should never ever use a delay statement in synthesizable code. You'll get differences between your simulation results and reality. Next one, here's a pretty simple module. Module, the name of it, right? So you could have chosen whatever name you wanted. Open up the port listing here. You're going to have input ports named as wire and a switch, right? And hopefully you've used what actually exists on our boards, I underscore switch 1. Output defined as O underscore LED 1. Closing parenthesis and the semicolon, super important. And then what do we want to do? We want to make an assignment, a direct assignment of OLED 1 to switch 1. End module, notice there's no ending semicolon. All right, last two questions. What does assign mean? Right. So is one-time computation? Is it something else? What is it? What meaning do you assign to the assign keyword? And question 5, does the order of these assigned statements matter? Right, I've got y2 equals a or b, and y1 equals a and b. All right, take a pause here, see if you can answer both of these. All right, so assign, it's a permanent wire connection. It's not one-time thing. It is continuously connected. It's like you have a physical wire between 2 points. The ordering does not matter, right? The hardware exists simultaneously. You could put these first, second, order it however you want. It will produce the exact same hardware. There's no change. So if question 3 was a little difficult, or if any of these were a little difficult, go rewatch video 3. Try to get a sense for designing a module. Look at some of those code examples. Basically get this down so that it is muscle memory, right? In terms of how do you define a module, the ports, and then things in between, the behavior of it. All right, so this is the end of day 1's recording. We're going to take a time tomorrow to look at data types and operators, focusing again on combinational building blocks. So you have the model. You have this idea now that Verilog describes concurrent hardware. We have 2 different tools or tool chains that consume our Verilog. We have the synthesis flow and the simulation flow. Modules, you can think of them as chips with named pins, or just some component that is physically there that has inputs and outputs. Tomorrow, we're going to give you more of the working vocabulary. How do you declare signals, combine them? By the end of the day tomorrow, you'll be able to get a hex digit on your 7-segment display. So you'll be using the real hardware, get some real output, all that tomorrow. So with that, looking forward to seeing you in lab, and we will go from there. Thanks again.